Good morning to one and all. In today's lecture, we'll discuss about the counters. Now, the question arises that what is counter? Counter is a sequential circuit that is used for counting pulses is known as counter. Counter is the widest application of flip-flop. So we can say that counter is the set of flip-flop whose state changes in response to the pulses applied at the input. The flip-flops are interconnected such that their combined state at any time is the binary equivalent of the total number of pulses that have occurred up to that time. We can also say that counter is a frequency divider. So basically your counter consists of two types. First is your synchronous counter and second one is your asynchronous counter. So, your synchronous counter in which the same clock is used for all the flip-flops. Your asynchronous counter, we can also call it as ripple counter or serial or series counter, in which out of one act as clock for the other flip-flops. Now, coming on to the difference between the synchronous counter and asynchronous counter. First, in synchronous counter, the same clock is applied to all the flip-flops at the same time. That means that we are applying the clock at the same time to all the flip-flops. Same clock will be applied. Second, it is faster than asynchronous counter because the propagation delay involved is less. Third is the design and implementation become tedious and complex as the number of flip-flops are increasing in synchronous counter. While in asynchronous counter, the output of one flip-flop acts as a clock for the other flip-flop. Second, it is slower than synchronous counter because the propagation delay is large and the delay increases as the number of flip-flops are increased in counter. So basically in asynchronous counter we are increasing the number of flip-flops, so there will be propagation delay, large amount of propagation delay will be there. And the last one, the design and implementation is very simple, even number of flip-flops are increased. So we can say that the designing of the asynchronous counter is quite simple as compared to your synchronous counter. Now we'll discuss about the asynchronous counter. So in asynchronous counter, the logic diagram, we'll see a logic diagram of a 2-bit ripple up counter that is shown in the figure. Basically in counter we use two types of flip-flop, that is your T flip-flop and JK flip-flop. Here we have shown in the figure with the help of an example of a T flip-flop. Here we have taken two flip-flops. The output of the first Q0 is connected to the input of the second flip-flop. So here we can see that your T flip-flop, both the input of the flip-flop is connected to a logic 1 and it is applied a clock pulse. So the output of the first flip-flop act as the clock pulse for the second flip-flop. Clear? Now the second is your synchronous counter. If the clock pulses are applied to all the flip-flops in a counter simultaneously, then such a counter is called as synchronous counter. So here we will be seeing with an example a 2-bit synchronous up counter. Here we have taken the JK flip-flop. So at the input of the flip-flop, here we can see we have applied the output of the J0 is given to the output of Q1, and here we have applied the clock pulse that is connected to both the flip-flops, and through K1 we have provided your logic 1. Now we will be seeing with the help of an example how we can design your ripple counter. So now we will be designing the 2-bit ripple up counter using negative edge triggered flip-flop. So here we have taken the JK flip-flop. Now here we can see the first flip-flop, that is your J0, K0, Q0 and Q0 bar represents the flip-flop 0. And the second one, that is your J1, K1 and Q1 bar represents your flip-flop first. Now here the question arises is how we'll connect both the flip-flops. So here, see in the question, we have to design two ripple counter. Means that we have to use two flip-flops. Okay. It is said we have to design an up counter using negative edge triggered flip-flop. Negative edge triggered flip-flop means that a clock pulse should be negative. A bubble should be applied before the clock pulse. Clear? Now here we can see that suppose in the mathematical terms we can say if we multiply negative sign then we get the positive, and if we multiply a negative with positive we get a negative sign. Clear? Now here we can see for the negative pulse it is represented like this, and for the so we call it as down counter, and for the positive clock pulse we represent it as like this. Now here we can see that we have to make a negative counter. Okay, we can see we have given a clock pulse that is negative edge triggered, so we can say the first input that is negative. If we multiply a negative with a positive then we'll get a negative one. Now we'll apply, it is said we'll connect your Q0 with clock pulse and will provide this as a clock pulse for the second flip-flop, that is flip-flop 1. Clear? So it will be connected in this way. Clear? A bubble will be applied over here and we can call it as flip-flop 1. Clear? Now coming on to the truth table. Here first we can say, first when we haven't applied any of the clock, the working of the flip-flop 1 is now dependent on the flip-flop second, the output of the flip-flop second, that is your Q0. Now here we see that firstly we have applied clock as 0. So initially your input Q0 will be 0 and your Q01 will be 0. So if Q0 is 0, Q0 bar will be 1, complement of it, and Q1 will be complement, that is your 1. Clear? Now in next, when we apply a positive clock pulse, now this symbol represents your negative edge triggering. For the negative we use as a down arrow to represent the negative edge triggered flip-flop. Now here previously we assumed that our output Q0 is 0, and we assumed Q0 is 0. Now when we have applied the clock pulse over here, if we apply the clock pulse over here, so what it will do, its function, we'll see that whatever input is provided at the flip-flop 1, it will give the complement of it at the output. So previously we provided 0, now we'll get the complement of it, that is 1. Now here we see for now the working of flip-flop 1. For flip-flop 1, the transitions should go from 1 to 0. This represents your negative transition, and when it goes from 0 to 1, it represents your positive transition. So here you can see that this is your negative edge triggered flip-flop. Okay, and we have got the transition is from 0 to 1, that is positive. That means it will keep output same, that is given at Q1. So the output will remain same, so it will be 0 only. Now when your Q0 is 1, so your Q0 is 1, your Q0 bar will be 0, and when your Q1 is 0, your Q1 bar will be 1. Clear? Now we have applied second pulse, we have applied second clock pulse. Now here we see the second clock pulse is applied. Now we'll complement the output. When we'll complement the output, we'll get 0. Clear? Now here we see the transition is from 1 to 0. That is the negative pulse, and it act on a negative edge triggered only because it is a negative edge triggered flip-flop. So here we see that the output 0 will get complement of it. So we'll get the complement of it, that is your 1. Clear? So your Q1 will be 1. Here we see that your Q0 is 0, so Q0 bar will be 1, and Q1 is 1, so you will get Q1 bar as 0. Now when we apply the third clock pulse, when we apply third clock pulse, it will at Q0 will get complement of it, that is 1. Clear? Now you see the transition is from 0 to 1. When the transition is from 0 to 1, that is positive, and we have a negative edge triggered flip flop, so the output remains same, so it will be 1 only. Clear? So your Q0 bar is 1, so the Q0 bar will be 0. Your Q1 is 1, so Q1 bar will be 0. Clear? Now when we apply the fourth clock pulse, we see over here, we at Q0 we'll get complement of it, that is 0. Now here we see the transition is from 1 to 0. Transition is from 1 to 0, that is negative, and we have a negative edge triggered flip flop. So what was the previous output? It was 1. We will get complement of it, that is 0. Clear? So we can say that when your Q0 is 0, your Q0 bar is 1, and when Q1 is 0, your Q1 bar will be 1. Clear? Now on basis of it, we'll draw the timing diagram. Now coming on to the timing diagram, here we have applied clock. See, this is called your positive edge trigger, and this is your negative edge trigger clock pulse. We call it as level. This is your up level, and this represents your down level. Clear? Now see, we have given clock. What we'll get at Q0? At Q0, till the positive, till the negative, the output remains same, and after the negative pulse, the output gets changed. What we are doing, we can see in the clock pulse that this is your positive side and this is the negative edge trigger, and we have to draw the negative edge triggered only. So at Q0, we'll see our output remains same, that is 0 only, because it is 0 and here it is 1. So it will remain 0 until and unless we don't get the negative edge trigger. After that, it will change, the timing diagram will shift, the bit will get changed, and up to so on. So what we can see that at Q0, it will remain 0 till your negative edge trigger occurs. After that, it will change its states. Then again, at negative edge trigger, it will change its state, then 0. After then, it will be 1, and after then, it will be 0. Clear? Now coming on to the Q1. Now the Q1 output will depend on the Q0 only. Previously, your Q0 was dependent on the clock pulse. Now the Q1, for the Q1, your Q0 is the output. Now it will act as the input for Q1. Here we can see that this is your negative edge triggered pulse, and here we get negative edge triggered. Now for Q1, it will remain 0 till we get negative edge triggered. After then, it changes its states, and then it remains 0. Clear what we did? That till here, it will remain in its same state, that is your 0. After then, it will change because we have applied a negative edge trigger. Its state changes. After then, here its state changes and we get 0. So this is how we design the 2-bit ripple up counter using negative edge trigger. Now in the next lecture, we'll see the 3-bit ripple down counter using the positive edge triggered flip-flop. Thank you.